This is my submission for fifth assignment of the NIC course, pattern identification using radial basis function and hierarchical clustering. So here is the question. The question is such that there are 7 patterns given, which if combined in a certain pattern will unlock the bank vault, and if not, then it will remain locked and give us the output 0. These are the given 7 output output patterns. 3 are for A, and 2 are for B, and 2 are for C. We have to fill 4 inputs. As you can see, we have total 7 patterns, out of which we have to take 4. So first 2 slots can be taken by the A group, which has 3 people, and the second has 2B and 2C. So total 4 possibilities. So if we see the total number of combinations, the first here it can take 3 places out of A1, A2, A3, and these 2, and this slot can take 4 values because B1, B2, C1, C2, and here 3. So the product is 72. So we have 72 ways to unlock, which gives output 1, and the rest will give 0, the locked state. There are such rules as if B or C comes first, then the condition is locked. If first A comes and then B or C comes and then second A comes, that is also a lock only. And if a random pattern comes in front of us, then also it is in the lock state. So we have just 72 ones. So here is the Python code I am submitting for the assignment. This code is written by me. I have not used any inbuilt functions. So basically what we have to do is we have to implement a RBF function with 4 Gaussian functions to implement these logics. For this we will require the hierarchical clustering scheme. We have to give input as 4 8-bit entries, and the output will be 1 if unlocked and 0 if it is locked. So instead of manually doing 0 1 and putting all that, I have find out the decimal values of that, and from this numpy library I can convert simply these decimal numbers to the binary for making the data sets. So these are the values, 3 values for A, and these are the 4 values B1, B2, and C1, C2, and this will be represented with with a bit length of 8 through this numpy module. So this is basically creating the data set in binary form of length 32, and after that we are giving some false cases, like all the possible 7 cases, something like that. So this will contain zeros also. After that we are adding some random points like randomly generated 0 and 1 in the population. This is also necessary for our performance. And after making all the data set, we will sort all the data sets such that all the 72 possibilities come at top. We have done this through np.unique, and what it does is basically it keeps this all the 72 ones at the top. The data set is made such like that. So if we want to see the data set formed, you can see here I am running the code half. So as you can see, this list H, this is of length 32, and number of columns is what we set here. I have set it to 150, and this is Python, so 0 to 149. This is it. After that, after creating the data set and the target values, we initialize the distance matrix with the Euclidean distances between the particles. As there are many points, 150 points in the data set, so we have to find the distance between each other particles, each with each other. So this is the initialization of distance matrix, and we have to make the diagonal values very high with respect to other terms, because afterwards we have to find minimum, and we should not keep diagonal values as 0, because the distance between with the self particle is 0. So after that we will implement the hierarchical clustering. So what we here do is we set the number of clusters to 4. So if the number of clusters reduces to 4, this loop will stop. So basically what we will do is we find the minimum value index, the index which has minimum value. We give it as fx and fy, and the and we stack these clusters together, and we keep the count of the total clusters left till now. This is agglomerate clustering. Basically what it does is it gives each particle a cluster and keeps on joining, and it will reduce to number of clusters to 4. So this is the main code for single linkage. This is minimum. So this is matrix values update. After that, after each update, we will remove that row and column from the matrix. So what we basically started with is, suppose 150 cross 150 matrix, we will get 4 cross 4 matrix at the last. As I run the code, you will see the df is initially 150 cross 150, something like that. After that, our df will get reduced, sorry, distance matrix will get reduced to 4 cross 4. After that, we have to find the all the 4 clusters formed. As you can see, these are the cluster 0, 1 and 2. Cluster 0 is basically first cluster, which is a nested list inside a list inside a list, basically, as you can understand. After that, we have to take all the elements out of this list. So we call the flatten function. This will get the list out of all the values out of the nested list inside the cluster. So we will get all the values inside the cluster, and after that we calculate all the centers of the clusters. So these are the center 0, center 1, center 2, center 3. After that, we have to implement the RBF algorithm as discussed in the class. For that, we have to implement phi equal to exponential of minus of x minus mu L2 norm square upon 2 sigma square. Setting, we set sigma as 2, we have set sigma as 1. These are giving us slightly different output, so sigma matters a lot here. And after finding phi, what we do is we find the w. W is basically pseudo inverse phi t phi inverse multiplied by phi transpose multiplied by the target. This is the w. The w we are getting here is like this 4 cross 1 matrix. After that, we test the algorithm on the train data set itself, and we will find the output here. So Python basically the output value comes in 10 to the power minus 124 like that. So Python basically finds the correct value. So we have to round, keep the np dot round value. We have to do that. So we, as you can see, norms here is what here we have get. This is our output. So what basically should have been, first 71 should have been 1, after that all 0 should be there. So we have got this good accuracy where many of these are 0 after 72. We have then calculated the mean square error after getting the output. Mean square error. So mean square error is basically norms minus ter square and np dot sum then divided by the total population size we have kept. We have kept 150 population size, out of which 72 were ones and rest were zero. So as you can see, as I am running the code here, my MSC is printed as 0.21 on the population size of 150. As you can see, after that, if I reduce the population size to like half or 80 or something, then my mean square error just reduces to very low, like 0.00 something. After that, this is my all code. After that, for dendrogram plotting, I have used inbuilt function from SciPy library. This is just to show you, this is not my implementation, this is SciPy implementation, and this will take some time. So basically we are getting an accuracy of 0.21 in on the population size of 150 or 200 or more. But when we are reducing the particle size, population size to like 100 or 80, we are getting very low MSE, like 2% or something, sometimes 1%. So this is my all code. This is a dendrogram from the SciPy library. So thank you. This is my submission.